Okay, here we go. We're into the double bonded functional groups now, and we're going to start with the first two families that contain a double bonded functional group. That would be the aldehydes and the ketones. And there's the functional group shown there. It's known as carbonyl group. So carbon with a YL, and so that's how you know it's an attachment or a branch. Just before I get started, there are just a couple of uses of these different types of molecules or compounds. Aldehydes used to be used in the manufacture of this plastic known as bakelite, and bakelite was actually formaldehyde, which is this particular molecule, and that is known as methanol, and phenol, which is actually, as you might guess, a benzene ring with an OH attached. It's an alcohol on a benzene ring, OH group. And so bakelite is actually a polymer, long chain macromolecule, but it would make this plastic, this brown stuff. And this brown stuff was very common as early as I think the 1930s into the 50s and early 60s as the go-to plastic for a lot of different electronic structures, electronic things like this old television. That is an old television. On the other side, we have ketones. So ketones, like this one, this is known as acetone. It's a ketone. And acetone is very soluble in water, and with a really low boiling point, it evaporates quite easily. And so it dissolves a lot of organic compounds. It's soluble in water and has a low evaporating or low boiling point, so it evaporates easily. So acetone, very commonly used as a solvent. And so as a solvent, like nail polish remover, it will dissolve off that nail polish, which is an organic compound, and then evaporate. So it's very useful in that regard. All right, so let's get on to this carbonyl group. So the carbonyl group is characterized by the C double bond O. And for aldehydes, specifically, it's a slightly different formulation. It has this attached hydrogen. So this attached hydrogen is very important. That indicates that it's an aldehyde. So this means it has to be a terminal group. The carbonyl group is terminal. It has to be on a terminal carbon, therefore it has that H attached. The R, then, as you probably already realize, can be any sort of carbon chain. It could also be an H, and that would be the simplest aldehyde, methanol, but it can also be carbon chains. The naming is very straightforward. We take off the E of our alkane root name, and we add the suffix Al. So here's an example. 1, 2, 3, 4 carbons. Notice the functional group is terminal, so that identifies it as an aldehyde. And this would be called butanal. And notice I do not have the indicate position of that branch because it's always going to be carbon 1. Here's another one. So there's my functional group, my aldehyde group, and that's carbon 1, 2, 3, 4, 5. So it's a pentanal, and on carbon 3 I have this methyl group, so it's going to be 3-methyl pentanal. Notice I do not need a number because it's always carbon 1 for an aldehyde. So that's aldehydes. Ketones, not much different, except the functional group, that C double bond O, is on what I term an interior carbon. It has to be interior, which means you have to have 2 R groups attached. These must contain carbons. So the first example of a ketone wouldn't be until you have 3 carbons. 3 carbons, that would be propanone. And the naming for the ketones is just as simple. You take off the E and you add the suffix -one, O-N-E. So let's have a look at this one. And again, here you do have to position the carbonyl group in the chain. This chain is going to be 1, 2, 3, 4, 5 carbons long. I have my ketone on carbon 2, and I have a methyl group on carbon 4, so this is going to be 4-methyl pentan 2-one. So again, the 2-one indicates the carbonyl group on carbon 2, because 4-methyl pentan 3-one would be an isomer. So that's why I have to indicate position of that that carbonyl group, the C double bond O. Let's have a look at this one. So here I have an attached alkyl halide, I have a ketone, and so I'm going to number this way to minimize the branch. I haven't changed the position of the carbonyl branch. So this becomes 1-chloro propanone. And again, I don't need to indicate position of the carbonyl group because propanone, it has to be carbon 2. If it was carbon 1 or carbon 3, for example, it would be an aldehyde if it was on a terminal carbon. Because it's in the middle, it's a ketone, and propanone, there's only one possible position for that carbonyl group. All right, so let's have a little bit more practice here. So again, here's my 1, 2, 3, 4. So that's butanal. I think we already had that one. Anyways, 4 carbons, aldehyde, terminal group. 3-ethyl hexane 2-one. Well, all in the name. So 1, 2, 3, 4, 5, 6. There's my hexane. Double bond O. There's my hexane 2-one. 3-ethyl. There's my 3-ethyl. And then I would maximize the bonding to carbon with hydrogens. Notice the group with the carbonyl group cannot take any more hydrogens. Now, you can also see where the problems might lie if you know the naming system. 2-methylpentane 5-one. 1, 2, 3, 4, 5. Pentane 5-one. Let's here put our 2-methyl there, and our pentane 5-one. And hopefully you've already seen the problem. The problem is that a ketone is not a terminal functional group, whereas here we have a terminal functional group. So this is actually an aldehyde. And so the correct name for this molecule is, in fact, 1, 2, 3, 4, 4-methyl pentanal, because it's an aldehyde. So that's correct. That is not correct. 3-ethyl pentane 3-al. Okay, so again, same thing. 3-ethyl pentane 3-al. So this would be a pentane 3-al with their carbonyl group, but that's already a ketone. And the other problem is 3-ethyl. Well, if you look, we have 1, 2, 3, 4 bonds already to this carbon. You cannot have a branch on the same carbon as you have a carbonyl group, because that carbonyl group is full, or sorry, the bonding to the carbon is complete. So you cannot have any more branches. So that name is just absolutely incorrect, so you can't even draw that one. Finally, carbonyl group and polarity. So a carbonyl group is polar, not surprising. The C double bond O is a polar bond. Delta En is about 0.8. And so aldehydes and ketones will have a bond dipole and hence a molecular dipole. So they're polar molecules. Aldehydes and ketones will have a higher boiling point than the same molecular mass or roughly same molecular mass alkanes because they're polar. So that polarity is going to make the force of attraction between molecules stronger. That said, the boiling point is going to be lower than an alcohol. And the reason for that is the type of intermolecular force. So because this is a polar bond, there's the polarity for both. You have polarity, but that type of intermolecular force between molecules is known as the dipole-dipole force. We're going to talk about these later, but dipole-dipole force is not as strong as what's seen in alcohols, which you already mentioned. Here's the polarity in the alcohol. That's known as hydrogen bonding. So hydrogen bonding is stronger than dipole-dipole force as a force of attraction between molecules. So the aldehydes and ketones of similar molecular mass than alcohol have a slightly lower boiling point. And so that's your introduction to double bonding functional groups, specifically the carbonyl group, and it's found on the two families we've talked about in this video, the aldehydes and the ketones. And that concludes this video.